Hello, let's consider how to work with this repository. It consists of Matlab files and of Unity files. Also has README file and Unity package file. So firstly, let's consider how to open this project with Unity. For example, there are several ways we can create a clone of this repository on your local computer. For example, copy a link, next create clone, and next locate where you wanna locate the project. So after that you will need simply download files using the fork. Or for example, you can download zip project and next unzip it. Also, this project was created with Unity version 2023.15f2. If you want to use another version of Unity, you can consider this import asset and download this asset. So you can click it and download. After downloading, you can create a new Unity project and next drag and drop this Unity asset here. Click import. And wait for some time. Next, find our scene CV system. So this is our scene we will work with, and also it has a resolution constant, this one. So you need to change the resolution to this one. And after that we can work with the project. So we can activate some obstacles, change the positions or reset them, checkerboards, obstacles, and also we need to activate the laser. So how to make it? It's also written on the page here. So we need to click File, Build Settings, Player Settings, Player Other Settings already, and disable it and activate OpenGL and move it up. So let's consider how to make it. So we need to click File, Build Settings, Player Settings, Other. Here we deactivate this toggle, add OpenGL core, move it up, and restart editor. And again wait till it will be loaded. So now if we start it, we will see the laser now belonging to the obstacles. So for example, we can rotate it, change the distance between camera and laser plane. So now it's activated, we can work with it. So that's how to import project to the Unity. Now let's consider how to operate this simulator in more details. So we will consider how to use it. So the simulator consists of two screens. Main screen, here we can change camera rotation, save images, activate, deactivate laser plane, change position, rotation, reset them. The CV system, in this case, we will move along XY axis the system itself. System means it includes camera and laser plane, so we move them together. Also can activate checkerboards, left, front, bottom, obstacles, left, front, right, and change their position or rotation. Calibration screen is the screen where we can calibrate the camera, obtain its intrinsic camera parameters. Here we can save image or can move the camera, change the position by moving it this way, or can change rotation or scale also with the mouse. It's also explained how to make it. Let's see how we can make it in Unity. So for example, here we activate some obstacles, change camera orientation somehow, and next we wanna save our image. We can paste the path here, or we can select it from here. For example, I wanna save image on a desktop. Next we give it a name, the default name, or change it. Also can change extension of the image, and next we can click save button. So we should see that our image was saved. So this is our image update from the simulator. So next we can proceed it with the MATLAB. Also we can reset these things, deactivate objects. For example, we wanna make the calibration of our camera, so we activate this checkerboard button and go to the calibration screen. So here we can move our camera. Currently I'm holding the mouse wheel button. Here I hold it, or I can click right mouse button and click WASD on a keyboard. Also the camera will be moved. Also I can change rotation of the camera and scale. So for example, I want to take screenshot of this image, change it name A1, and again I want to save it. So we should also see it on our desktop. So this is A1, our obtained image. In the project we can also change the quality of our camera. For this procedure we need to find this texture of our camera and change the size. For example, if we will increase it, the quality of our camera will be better, but also it will consume more, it will be more consuming, this app itself. So if you don't have a powerful computer, so it's better to not change them or decrease them, but also do not decrease too much, because the quality of the image won't be really well. But for better calibration you can increase them. So that's how the main idea, how to operate with this simulator. Now let's consider the intrinsic calibration of our camera. So how to make it? It's explained in this PDF. So firstly, preparation, we need to follow this idea. It was proposed by David Scaramuza, and from this source, according to this source, we need to take from 6 to 10 images, and also some advices how to take these images. We have our fisheye camera, and we need to cover all of the lens. For example, we need to take put this checkerboard here, next move it here, here, here. So this way we cover all of our lens. If we will just take screenshots of our checkerboard in one area, it won't be really good. So in this case, we won't get reliable calibration results. So for better calibration results, we need to cover all of the lens. So also for this tutorial, we will use the extension provided by Stefan Urban. So according to the paper, by this extension we can obtain more stable, robust and accurate calibration results. So next, the installation process. We need to download OCam calibration toolbox provided by David Scaramuza, also extension provided by Stefan Urban. So this following links we need to follow and download these files. So once we download them, we need to replace files in the main directory. And next, the calibration procedure itself. So also you may not, it's not really needed to download them because these files already located here. You can find them replaced here and just put your calibration images to this folder. So let's consider this MATLAB folder. For how to use, we already considered it. I can close it. So here what we need to start, we need to run OCam calib urban. So this file we need to run, but firstly we need to take calibration images by the simulator. So I will use these images. So it was already taken. So these images I will use for the calibration. And you need to give them same name but different suffix. For example, A1, A2, or image 1, image 2, image 3. So next, let's find the file. OCam calib urban. And move it to the MATLAB. And run it. So firstly we need to read names. Here we put the name without the suffix. For example, we have name of our images A1, A2, A3. So without suffix means just A. So I will put A. Next we need to specify extension. Here we work with the JPEG images, so we need to put J. For example, for other format, different letter. Here is J. So images will be loaded. We can move to the next step. Next we click extract grid corners. For all images just click enter. Next, number of the squares along x direction. Here it's mentioned that we need to select 5, and for y direction it's 8. For example, y5. Here we work with this region 1, 2, 3, 4, 5. It's x direction. and y direction 1, 2, 3, 4, 5, 6, 7, 8. So that's why. So along x direction we put 5, y direction 8. Next, the size of each button. So the size means size of each of the square. It's mentioned here. It's equal to 116, 116. So same we put to the MATLAB. And here the center. So we have the image with the following resolution. So simply it's divided by 2. So we just click enter and enter. We do not change center. And here is also enter. Next we wait till our images will be proceed. Here is the x direction, y direction. And we extract these image points. So once we know these image points, we can find the location in the world coordinates. And if we know world coordinates, we can calculate the intrinsic parameters of our camera. So we know image points, world points. And based on it, we can obtain a relationship between image points and world points. So we finished with the corner extraction. Next we go to the calibration procedure itself. So we click calibration, and after that we also need to click robust non-linear refinement. Firstly, the calibration. Here click enter and wait. You see busy, so we need to wait. And also the robust non-linear refinement. So it was finished. Now we can save our results. So we click the save button. And this is the results we've just obtained. So I have similar results here, I just renamed them. So I will use these calibration results for the rest of the tutorials. So now let's move to the next tutorial, on how we can estimate our intrinsic camera calibration parameters. In real cases, for this procedure, usually use the checkerboard. For example, as for simulation environment, we can know where all of the objects located and their particular distance. But in real cases, we need to use some measurement device to obtain the distance, for example, the ruler, and measure this distance manually. And it can be not really accurate. So in real cases, for getting the known distance, usually chess pattern is used as a ground truth. So let's make some same procedure in the simulation environment and use this chessboard pattern for obtaining distance to the obstacles. And here we also know this distance, so we will use it for estimation results comparison. So firstly we prepare two images of the up chess pattern and left chess pattern, and next we go to the main program. So firstly we here clear console, clear workspace, next load our calibration parameters, open camera model, and what we do next is to add our calibration images to already existing ones. Next we extract points of our chess pattern, image points. So idea here again to obtain a relationship between image points and world points. And for this procedure we calibrate our image and next find the transformation matrix. It will show us the relationship between image points and world points. So from this matrix we can get the distance between camera and checkerboard pattern. So here how we extract this distance from the transformation matrix. And same for the second image. Just the difference here between this part, because in first case we estimate distance along one axis, and in second case we estimate distance to along another axis, for example here along x-axis, here along y-axis. So that's why here are different indexes. So now, and in the last part we estimate, do the result comparison. So here's the distance to the left chess and here's the distance to the up chess. And here's the experiment values. And actually here we've got better results even if the chess pattern located more far. We obtained more accurate results. Maybe just because here the chess pattern is more visible and here it's more the angle view. Maybe because of this. Let's start the MATLAB file. CalibBasic, it's this tutorial CalibBasic. Firstly you need to add images here. After that we need to also copy these two files from our calibration tutorial. This file CalibData and this file you need to use for the rest of the tutorials. So this two was copied also here. So next we just start this tutorial. First image will be opened and proceed. Next we open and proceed the second image, and as a result we display the distances y1 and y2 from the first and second. So this is an example of the second transformation matrix. So from here we obtain this distance to the left chess. Getting started basic. In this tutorial we will locate 3 obstacles. Also in this case camera is not rotated, and here we just rotate the laser plane by using these parameters. So these two we change respectively, and distance is this distance. So this image we need to save. What we wanna do here is to measure distance to these objects. Firstly, we need to clear everything and load our image. And here we firstly do the laser segmentation. For the theory, we can visit this source and read how we can extract it. So we extract our laser by its red color. So the benefit of using the laser, because in the environment, for example, we can usually have not too many red colors. So by using red color, we can simply detect it and extract. So here we do it by threshold, and so here also this value you need to play if you have any other laser color or intensity. So here how the result will look like after this extracting operation. So here's our result. Here we can see laser belonging to this obstacle, to the up obstacle, and to the right obstacle. So next we do the mapping. So here we load our calibration parameters. Also we know the laser plane orientation and distance. Here we didn't move our CV system, so its location equal to 0. So our region is located at camera, so coordinates 0. Next, how the mapping function is created. Here is for this theory, how it was made. We can visit this source. For example, you can read this paper. Here is shown the relationship between the image points of the camera and world points of the camera. So image points and world points, they related through the camera orientation matrix and laser transformation matrix. So this means that in real cases the camera may have orientation. In our case, for this basic tutorial, we didn't rotate our camera, so it will be just identity matrix. But here we rotated the laser plane. So here we'll need to obtain the rotation matrix of the laser plane. So it's also mentioned here. So our laser has distance between camera and laser, and we need to compose rotation for our matrix. So if we also drag and drop this tutorial, CalibBasic, here open mapping function, here open compose rotation matrix, we will see how this matrix is composed. So here firstly we composed particular for rotation around x, y, and z, and next we firstly multiply z by y by x matrix. So that's how we obtain the rotation matrix. So once we compose them from the model, we can calculate the world points. These world points are distances to our obstacles. So here also mention how to calculate them. So here firstly we know that this z coordinate is constant, is the distance to our laser between the camera. So this one don't change, the changing just these two along x and y. So this one is a constant, between camera and laser, so we can remove it from here. So this one is actually 0 because it will be taken from here, from the transformation matrix. So it belongs here. So this one is don't change, so it's equal to 0. So that's why in this formula we don't have the z coordinate, and actually just the column 1 and 2, the column 3 will be deleted because of this coordinate. So if we do a multiplication between these matrices, we'll see that this column will be removed. And next we combine this camera laser matrix in one, so this is one resulting matrix. And after do some mathematical operation on this, we can obtain the x and y coordinates. And again, z coordinate is known, it's the distance between camera and laser. So after that we just get back this world points and do the mapping. So as a result we'll see these world points. So this is the distance to our right cube, left cube, up cube. Next we also can do the results validation. For example, these parts may have some noise. We can just take all of the points here and take the average value. So that's how we will eliminate some noise. So for this procedure we also need to know this image coordinates. So we will just extract this part by putting particular image points, and next get the average value by similar mapping function, and here get the mean value. So for example, let's consider this considered steps. So I will run this file. Firstly we extract this image, get the mapping. So how to obtain these image points? So we have, for example, this plot. Here we should see the these data tips, and it will show us particular pixels. So we are interested in this rectangular, so we extract similar points, or here, from here to here, this point, here from here to here. So this we use in our program. And next we fill these regions. So we want to work just in this region and obtain distance and get the average value. So this is for the left, for the up, and for the right. So we do so what we do here, again we do mapping and obtain the average value. Here we know the real values from the left cube, up cube, and right cube. Again we know it from the Unity to the left, to the up cube, and to the right cube. And what we've got in the Matlab, to the left, to the right, to the up. Also we compare it in this file. Experiment values, and we subtract them. So this is the result for the tutorial basic. Next, let's move to the next tutorial intermediate. So we close this one. So what we do here we also rotate the camera, and also we rotate the laser. And here we will also move the CV system to another position. So we want to obtain the global map, like the vacuum cleaner robot move along the environment, and we also move the CV system, and we want to obtain and build the global map. So we need to take the first image, next move the CV system to another place, and take image as well, and we need to write down this position of the CV system and its rotation of the CV system. It's also mentioned here. Next, again, we firstly do the laser segmentation for our first image, second image. This is the first image, this is the second image. So we extract laser from the obstacles. Again, use similar function for the laser extraction. Use threshold to extract the red laser beam. Next, we define our known parameters for the camera, for the laser. It's the first CV system point. So in previous tutorial we didn't move our CV system, so its coordinates was 0, 0. In this tutorial, intermediate tutorial, we also move CV system, so it has coordinates, these coordinates, and this rotation. And next we do mapping function for our first image and second image. And as a result, we will get these two maps here. So the blue color corresponds to the first image. So for example, this, we cannot see other side of the cube there, so this orange is for the second image. So we combine them, so now we have more data on our obstacles. For example, before we didn't see the back side, now we see the back side of our cubes. And next, how we can also measure distance from this to goal. So let's consider it. So I will drag and drop this intermediate tutorial, run it. So we can estimate distances from here. Interested for us. So this way they were written manually and estimated here. So this is the real values from the Unity, this experiment values from this plot, and errors, what we'll get. Also in millimeters. You can see it was also pretty accurate, as 4 millimeters, 5 millimeters, even 15 millimeters. It's not a big error. So, and in this case, we also rotated the camera, so we have here composed rotation matrix of the camera and laser. So exactly this theory. So our image points and world points, they were related with the camera rotation matrix and laser plane transformation matrix, which consists from rotation matrix and translation matrix. So here we put distance between camera and laser plane. So this distance is known, it's don't change. Again, it means that this coordinate equal to 0, it's taken from here, this distance, these two coordinates is changing, so that's why here we only work with x and y, that is 0. And we do mathematical operation, and from here we find the world points x and y. So that's what about the intermediate tutorial. Now let's move to the last tutorial, getting started advanced. This tutorial is about calibration of the vision system. In previous cases we worked on the known parameters, known orientation of the camera and laser plane, and also distance. So we worked with it just to understand how to compose these matrices, but in real cases it won't be possible to know the distance between camera, laser plane. Now, for example, we can measure it manually, but we can get some errors. Also, we won't know the camera orientation, real camera orientation, and real camera and real laser plane orientation. So we can get them with calibration data. So how to do it? For this calibration procedure, we will use two perpendicular checkerboard patterns, and here we need to take two images. For example, the first images we'll need it to get image points of checkerboards, and this image will be needed for the laser extraction, and this one we will use for estimating the calibration results. We will also rotate camera by 1, 2, 3 and laser plane and change its distance. So same here, we need to save these images with the same rotation, translation parameters. These three images we need to save, and we will compare this data also with our calibration data. So firstly, how to do the camera calibration. This is our known angles. We will use it for comparison procedure. Firstly, we load our intrinsic parameters. Next, we need to extract our image points. So firstly, we get some points of our checkerboard. For example, firstly we've got these points. We next put some color on them in order to extract the second points. So that's how so for this procedure, this function was created in order to get the second pattern points. So we've got first image points, second image points. Next we do calibration, get transformation matrix between image points and world points, and next we project our checkerboards to the world points. Here we manually put our data equal to 0. This means that our camera is not rotated, so we will see these angles. So if our camera is not rotated, we can obtain these angles. For example, this rotation, this rotation. So you can see the offset here. So here, how by this geometry we can find these angles. So for example, if we draw a line here, so we will find this angle. Also this angle, can find. So these angles we are searching for by the and also this angle. So we need to find them. And here they are found by the geometry. So we take these points, angle, these points, some other points, and calculate them by geometry. So this is our points. We just do similar things, looking for the angle. So once we found these angles, we can, they are stored here, we can project our data later again. So this is our angles, and this is how we determine the orientation of the camera. So this is the known, this is the experiment results. We obtain them from here and take the mean value. And this is the error, so it was accurately found. Next we project it again, so now we see that it has a perfect structure. We don't have any other unnecessary incline. So we project it again by knowing the distance to the chest pattern, its rotation. We've got this. So this is our known distance, this is the experiment distance, and this is the error. Next, the laser plane calibration. So firstly we do the laser extraction. We extract laser from our image, and next we wanna extract laser belonging to left pattern and up pattern. So we will project it separately to the world points. So this is a function which extracts separately two laser belonging to the chest pattern from the up side, left side. So this is two separate image. And next we project them to the chessboard pattern just to for better understanding. So this is our chest pattern, one of them. This is the second pattern, and this is how the laser belong to them. Next we, in order to find orientation of our laser plane and its distance, we just fit the plane to these laser points. So once we fitted the plane to our laser points, we can get the orientation of this plane and its distance between camera and laser. So this is how we can calculate it. Also, this source can be visited. It's explain how to work with the plane in MATLAB. And so after that, after this mathematical operation, we will get the orientation of our laser plane and its error. So this real values, actually here 1.5 and here 2.5, and errors. So once we obtained our parameters for camera rotation matrix and laser transformation matrix, we can make a mapping verification. So we load our test image, this image with the obstacles, and do mapping verification. So here again we will apply camera rotation matrix, laser transformation matrix, compose two of them again for the very brief theory. So here the relationship between image points and world points, they related with the rotation camera matrix and transformation laser matrix, and this distance not changing. The Z1 it's taken from the transformation matrix of the laser plane and equal to the constant value. So in world points we only change these two values. This one is constant. So that's why we don't have that here and work just with column 1, column 2. Here they multiplied with each other, these two. So we have just one homography matrix, and after cross dot product we'll have this data, and we can find from the x and y world coordinates. So same here. So we can see from this plot that we, with our data, found this global map correctly. For example, if we put some 0 points to our matrix, mapping matrix, we will get the wrong plot. So that's why the calibration procedure is important. We need to know the camera rotation matrix and laser transformation matrix. Otherwise we will get the wrong plot and we cannot work with this mapping result. And next, again, result validation, how to make it. We need to know these image points, then we eliminate some noise, take average value and estimate distances. So this is the final distances after the mapping. Again, let's run this tutorial. So let's run this tutorial. So firstly we proceed this image. Next we put this blue data here. So next we proceed this image. Extract laser points. Next, laser points belonging to the particular chest pattern. And mapping verification. So again, one more time, how we get these points, image points. Here in Matlab we look for tools, data tips, and we click regions interested for us and write them to the Matlab. This x, y image coordinates. So we put them here for the particular cube, and here's our final results. Also here it shows step by step. Here also to the laser points it was fitted there also average least squared line to eliminate some noise, and here's the projection, here's the fitted plane, and here's the final global map. So that's all for this tutorial.